Yes.
Yes. Okay. Awesome. All right. So our project topic is called analysis of file dependencies to enhance the system reliability. The idea here is basically that certain files are extremely transitory in their lifetime in the file system, and then some some files are sort of dependent upon a lot of others. So, for example, when you compile like a C project, from like a .c file, you create like a .o and then the a dot out. So the idea is basically like the .o isn't necessarily as important as the .c because it can be regenerated later. And so the idea is we're trying to look at file system dependencies within the system. We'd like to determine sort of what's kind of the most important by deciding sort of like what should be preserved and what can be easily regenerated. And so what we found is there were some sort of dependency tracings and some other papers we read. For example, the first paper mentioned here used a system call fuzzer. A fuzzer, basically its input to follow execution paths that was used. The file system dependencies with feather stitch had some rules built in. But our project here is kind of more of looking at the traces and seeing and by manipulating traces to see like what has like the least overhead. We're not actually directly interfering with the system. We're planning to use tools like strace and debug fs for this project. We did reach out to Bobby Roy, who works here at computer science at Florida State, for help, and we're currently waiting for him to get back on us with help with some more tools. So I guess Vincent, go ahead and take on the methodology.
All right, with methodology, a quick definition for file dependency, like relationships where targets depend on sources and are usually created from them. And there's what he already talked about with the C source code files, then the object file, and then the linker creates the executable. And then we will use the strace system call and its ability to intercept and record the system calls, and we will use strace to view file dependencies to determine the importance of files. And then we will also attempt to replicate important files as well as randomly corrupt blocks to replay traces and to see how many executions were successful. And from there, we can construct a dependency graph from our measurements. And then our evaluation of success, we're just going to determine how much of the reliability of the system has improved, compare the percentage of corrupted data blocks versus the percentage of the successfully replicated strace, create a dependency graph to visually demonstrate the results. And our end goal is to demonstrate that the file systems can be more efficiently used with less overall copies of files and data.
So in the case that we can't have reliable dependency graphs, we're going to apply deep learning as our plan B from the data sets created by the traces. And this can allow for a model that basically intuitively recognizes file dependencies and usage. And here's a general timeline. We're mostly going to be initially focusing on setting up the simulator. And then from there, we'll start collecting data on the traces and basically the dependency graphs, and then from there we can start to evaluate our results and begin writing the report. And here's our division of labor. As of right now, we're waiting for the simulator setup from Bobby Roy, and then from there we can get started on each of our individual tasks. And then here's our references, and yeah, thank you so much.
Thank you.